We have talked about two of our three approaches to mechanics, two of the three ways we have in this class of solving mechanics problems. We've gone through Newton's laws, we've gone through work and energy, and now we're going to start talking about the third approach, momentum. If we write down Newton's second law, the way we've expressed it so far, it tells us that if we add up all the forces acting on an object, so we have the net force there, we have so far written that it equals mass times acceleration. When we first wrote down Newton's second law, we said that this was only true if m, the mass, was constant. If you have a system where the mass varies with time, for example, a rocket, so that it's burning fuel and has less mass as time goes by, as some of the fuel gets shot out the back end, then this equation can't be used. The way Newton originally wrote down his second law was in a more general form, like this. He said if you add up all of the forces on an object, so that you have here the net force, the net external force, what you get is the rate of change of what could be called the quantity of motion. You get the rate of change, d by dt, the time derivative of what we could call the quantity of motion. Quantity being the mass here, and the motion is the velocity. Now, if the mass is constant, it could be dragged out of this derivative, and we would have mass times the derivative of what's left, the velocity, and that gives us sum of the forces equals ma. But this equation is true in general. If you add up all of the forces on some object or on some system, it tells you the rate of change, the time derivative, of this thing in parentheses there, mass times velocity. It used to be called quantity of motion, and it's a good name. But nowadays, for whatever reason, we call this thing momentum, and we identify it, for reasons I don't know, with the letter P. So P is momentum, mass times velocity. So we could finally write Newton's second law this way. If you add up all of the forces on an object, it tells you the time derivative of the momentum. An important thing about momentum is that it's a vector. In the last chapter, we got away from looking at vector quantities for the most part, and we were interested in speeds and scalars and all of that kind of thing. But vectors have returned here, and one of the things that we have to pay the closest attention to as we go through this chapter to avoid making errors is to remember that momentum is a vector. As we're in class and we're solving problems, I'm going to remind you so many times that momentum is a vector, direction matters. What is this momentum telling us? Suppose we have two objects. I'm going to draw a baseball and a rock, which is much larger and has more mass. So this guy has mass little m, and this guy has a much bigger mass, capital M. Suppose both of these things are moving at the same speed in the same direction. So somebody throws this baseball at speed v, and this rock is also going at the same speed in the same direction, speed v, in that direction. Well, these guys have a momentum, a quantity of motion that depends on two things. It depends on their speed and direction, and it also depends on how much stuff there is moving in that direction. The more stuff you have going in that direction, the more momentum you have. So we could draw these momentum vectors. Maybe this baseball has this tiny little momentum vector, P, and this rock, because of all its mass here, there's a whole lot of stuff going in that direction, it might have a big momentum vector, P, going in the same direction. So notice that the more mass you have, the more momentum you have in a certain direction. Also notice that the momentum vector is always in the same direction as the velocity vector. This vector p is always going to be parallel to this vector, the velocity. The momentum is a vector in the same direction as the velocity, with a magnitude scaled by the mass. We tend to solve two kinds of problems. We tend to do two sorts of things in this chapter. What I want to do in this talk is to introduce you to those two things, and then we'll look at each of them individually. So the two things that we tend to do. Number one over here, and number two we'll put over here. All right, the first thing we tend to do is to take this equation, and suppose we know the force as a function of time. We're pushing on an object, we're making it move, and we want to know then something about its change in momentum, or either its initial or final velocity, some piece of that change in momentum. The way we can get at that is by bringing this dt over here and integrating this equation. Newton's second law can be written this way. dp equals the net force times dt, so that if we integrate this equation, which is to say, suppose we have some force acting on an object, and we let that force act for some amount of time. We can start it at t equals 0 and go to some final time t. Then what that does is it changes the momentum. The force acting on the object for some time changes the momentum. So the momentum would go from some initial value to some final value. And when you integrate this, what you get is what's called the impulse momentum theorem. On the left-hand side, we just get the change in momentum, p final minus p initial, that's delta p. And on the right, we get the integral of the net force acting on the object over time from 0 to t. This is called the impulse momentum theorem. In the next talk, we will go over this guy. We'll rewrite this and look at some of the more familiar ways that we express this, but this is how it is in its most fundamental form. And what we tend to do here are things like, suppose you know what the force on an object is, find either the change in momentum or the initial or the final velocity, some piece of that change. That's one kind of thing we tend to do. Another thing is we tend to solve problems where we know what the change in momentum is, or we can figure it out, and we know how much time some force acts. We can then solve for the force. So we either tend to dig this force out and solve for it, or we look at some piece of this change in momentum. So that's the impulse momentum theorem. We'll talk about it in the next talk. But that's one thing we tend to do with this version of Newton's second law. The other thing we tend to do is to take Newton's second law here and apply it to a class of problems that turns out to be pretty common. If we can find an object or a system or anything that has no net external force acting on it, so that if I take that object or that system or whatever and I add all the forces up, if I get 0, then that tells me something about the momentum of that object or the system. If the net force acting on something equals 0, then the time derivative of the momentum equals 0. And you know that if the time derivative of something equals 0, it means that thing is constant in time. So if you can ever find an object or a system or anything that has no net force acting on it, then you know that the momentum of that thing is not going to change. If you can figure out what the momentum is at some initial state, you can set it equal to the momentum at some final state. And this we typically call a conservation of momentum. So the other kind of problem, the other class of problems that we get led into in this chapter are problems where the momentum is conserved. All right, in the next talk, we will look at the impulse momentum theorem. We'll rewrite this in a couple of ways, and we'll look at some examples.